plus 2. To contribute to 4n plus 2, you actually have to be in the ring. So these don't contribute to 4n plus 2, so this is still going to be 6 electrons. But what this does do is it adds electron density into the pi system. So it doesn't contribute to aromatic or not aromatic. It just makes it just adds more electron density to the system. So this will still be aromatic. And so the first thing you can do is you can draw a resonance structure where you dump this electron into this bond, causing this electron density to kick into here, and that will give us a resonance structure that will look along the lines of this. All right. So now, from this doing this, and a positive charge on nitrogen, we have a minus charge at the first ortho position. And we can resonate this electron density further to this carbon. Like so. And of course, then we can resonate this minus charge to this other second ortho carbon. And of course, the resonance structure I'm drawing now is exactly the same as this resonance structure by symmetry. All right. So in essence now, with this nitrogen adjacent to here, we have 4 different resonance structures. And what we end up getting is a resonance hybrid where we have a partial minus charge here, a partial minus charge here, and a partial minus charge here. So this explains why electron donating groups are both more reactive, because they're putting partial minus charges in the system, and partial minus charges are going to be more reactive than carbons without partial minus charges. And it also explains that same thing, partial minus charge, carbons with partial minus charges are going to be more reactive than carbons without partial minus charges. That also explains why we get ortho-para direction, because the ortho and para positions have partial minus charges, and the meta positions have no partial minus charge. So in essence, we're activating the homos of the ortho and para position by putting more partial electron density there, where we are not touching the meta position. So, does the camera get this board?
Yeah.
All right, great. And so this is with an electron donating group. So we have partial minus charges here. Now let's do it with an electron withdrawing group. Someone tell me an electron withdrawing group to do the example with.
Nitro.
Nitro? That's a good one. So EDG, and this green is not that good. Okay, good to know. And now let's do analysis of EWG. So here's a nitro group. A nitro group is one of the most electron withdrawing groups you can get. The nitro group is one of the most electron withdrawing groups you can get. For 2 reasons. Obviously, as I'll show you, there's a big resonance component. There is a very big resonance component. The other thing is, this nitrogen has a positive charge. Right? So since there's not only is there a big resonance electron withdrawing effect, there's also a big inductive because of the bloody positive charge of the nitrogen. So the resonance analysis I'm going to show you will be identical to that of a carbonyl. Because if you think about it, right, this nitrogen-oxygen bond is kind of like a carbonyl, right? It's carbonyl is going to be less electron withdrawn because the carbonyl carbon doesn't have this explicit positive charge on it. But still, the resonance analysis, electron pushing-wise, is going to be identical. So I don't think there's any secret what's the hybridization of this nitrogen. sp2. Not only is it in a double bond as drawn, it's also overlapping, so it's very much sp2. The nitro group, since I just drew this in 3 dimensions, I'll just draw it real quickly. So the oxygens are in plane with the ring, since it's sp2. And then I guess we have some kind of anti-bonding orbitals that you could argue are going to be roughly overlapping with the so nitrogen, oxygen, pi star orbitals. So NO pi star, my nitrogen should be uppercase, not lowercase. And there's a minus charge here, positive charge here. So we have these empty pi star orbitals on the nitrogen, which are ready to suck in electron density. So so what this means, since these empty orbitals, pi star orbitals, overlap with this pi system, it means that resonance is it's not possible, but it means it can happen and it will happen. So the first resonance structure you can draw, just as before, is this bond going up in the nitro system. Minus, minus, positive charge here. Now there's going to be a positive charge here. So now, the first ortho position, we now, instead of having a minus charge, like with an electron donating group, it now has a positive charge. And you can, of course, resonate around the ring, just as before. They have the 3 resonance structures, just as we drew before with the electron donating groups. But this time, instead of having partial minus charges, we now have partial positive charges. So what that means is, in a resonance hybrid, for an electron donating group, or withdrawing group exemplified by a nitro group, is that we now have partial positive charges at both ortho positions and the para position. So partial positive charges at the shoulders and toes, and I guess the knees will have no partial positive charge. So the knees aren't untouched. So this explains A, why electron withdrawing groups are less reactive. They're less reactive because we're now putting partial positive charges, or in other words, we're removing electron density from the pi system. So that's why they're less reactive. And then we are also specifically putting the partial positive charges via resonance at the ortho and para positions. And just as in this case, carbons with partial minus charges will be more reactive than carbons without partial minus charges. Carbons with partial positive charges are going to be less reactive. than carbons without partial positive charges. So because of that, that is why electron donating groups go meta. Because the meta positions aren't touched. The meta positions have the same amount of electron density they would have before, whereas now the ortho and para positions have less electron density. So for electron withdrawing groups like nitro or carbonyls, what we're actually doing is we're deactivating the ortho and para positions. And so it's going to go meta by default. So the electrophile, when it's looking at an electron withdrawing group on our thing, it's looking for what's the lesser of two evils. Really unactivated or just not activated. It's going to go for not activated over unactivated. And so that's why electron withdrawing groups go meta and para. Does the camera get this? Like. So I'm going to give you some numbers right now. Some ratios of ortho to para to meta. Just to really bring this stuff home.
So electron withdrawing groups only meta, right?
Yeah, they prefer meta markedly. Oh, I'm giving you some numbers right now that are from the notes. And so this data is for the nitration of various benzenes. So it's nitration, so it's going to be HNO3 and sulfuric acid. And you can of course get ortho nitro, meta nitro, or para nitro. So ortho, I'm going to do ortho meta para in a different color. Why? Because I can. Ortho meta para. All right, and the various possible substrates we're going to be looking at is a methoxy group, toluene, so just a methyl group, then we're going to look at chlorine. Well, first off, let's get chlorine and bromines for now. Let's just go straight to CO2, to the carbonyl. So benzoic acid. And then finally we will do, let me redraw it so I'm over at the bottom. Then finally we'll have nitrobenzene. Right. So let me give you some basic reactivity profiles. So first up, which one of these is going to be the most reactive? Methoxybenzene, methylbenzene, benzoic acid, or nitrobenzene. Which one's going to be the most active? That's going to be methoxy, right? So methoxy should have a relative rate of, I had this in my notes, but I'm so unorganized today at least, and I apologize. I can't seem to, should be in 15.5. 15.3, 15. Do I have it? All right, yeah, I got it. So first off, let's also throw in benzene. So if our relative rate, so in red I'll write relative rate. If we set benzene's rate to 1, so if we set benzene's rate of nitration, so just R equals H, to 1, with the methoxy group, we are 1,000 times faster. So a methoxy group here is 1,000 times faster than in hydrogen. So a methoxy group activates this reaction 1,000-fold compared to compared to benzene. The methyl is roughly 100, I believe. Don't quote me on it, but I believe it's roughly 100-fold. The nitro group is going to be 0.0000, a lot of zeros here, 008. So this is that much slower than benzene. So the rate of this is 0.000008 of benzene. So again, electron withdrawal is really sapping electron density from the system and making it slower. I don't actually have the data for carboxylic acids, for benzoic acid with me, but it's going to be something like 0.01 or something along those lines. So I'm going to just do a tilde and 0.01. And if anyone sees this online and I had the wrong number, I apologize. But it's going to be significantly less reactive than benzene. So now let's talk about the ortho, meta, the para ratio. So for the methoxy, we get 44% is going to be ortho. And 55% is going to be para. Is this surprising? So there's 2 ortho positions and 1 meta position, right? So if they're equally reactive, we'd expect to have a 2-to-1 ratio favoring ortho to para. But we're actually favoring para, right? So statistically, para has to be at least twice as reactive as the ortho position. Because there's 2 ortho positions, there's only 1 meta, yet there's only 1 para, yet we're still getting para over ortho, so we're overcoming statistics. Based on this, why do you think we favor para slightly over ortho? Sterics is a great answer. Sterics is great. Sterics is very, that's the right answer. Another thing to think about though is, when we have a positive charge on the nitrogen and resonance structures, right? So this nitrogen has a partial positive charge. Okay? And so now you could also argue that there's a slight inductive effect that's counteracting the shoulders or the ortho positions. And since the inductive effect falls off with space, so it falls off R to the 3rd, so the further away you are from the inductively withdrawn thing, the less of an effect it has, you could definitely argue that in addition to sterics, the ortho positions are also slightly disfavored because of the slight inductive effect from the electronegative electron withdrawing group. But you don't go around the sterics. But you won't go around with the inductive effect as well. So methyl, the methyl group, now gives us 55% ortho and 38% para. And in theory, it gives you about 4% meta. Don't worry about the meta, that's 4%. So now, this ratio we get for methyl, does this agree or disagree with the sterics argument? It slightly disagrees because methyl is actually bigger than the methoxy group. Because the oxygen and the methoxy group just has 2 lone pairs of electrons, whereas the carbon has 3 hydrogens, so methyl is bigger. Yet, now we're favoring ortho over para. So that disagrees with the sterics argument. But does it agree with the inductive effect argument? Absolutely, because the methyl group never has a partial positive charge. So this methyl group favoring ortho over para actually suggests that the fact that with the methoxy group we favor para over ortho is actually due to the inductive effect rather than sterics. I still like the steric argument. but I just wanted to illuminate that issue. Now let's look at the ortho-para for carboxylic acid. For carboxylic acid, we now get 80% meta, 18% ortho. There's some shenanigans at play for why we get 18% ortho. I won't go into it because it's above the pay grade of this class. But the thing I want you guys to realize is the major product is meta. And we have 2% pair. So when we go to a weaker but still an electron-withdrawn group, now we favor a slower reaction with meta. And then finally, with the nitro group, we get 94% meta, and then, boom, 6% pair. So really slow reaction, but the more electron withdrawn you are, the more meta you get. So let me end the last 5 minutes. So I think now, I build a very nice argument up, right? It's all right, electron withdrawn groups withdraw electrons, put positive charges in ortho and para, so it goes meta. Electron donating groups donate electrons, put partial minus charges at the ortho and para, so it goes ortho and para. And, it's always be a mixture between ortho and para, but, you just live with it. And the exams will make it clear if everyone ortho or para. If I don't make it clear, just drop out. So now let me throw a wrench, just because I like to throw wrenches in things, because that's how I roll. You know what the sound of scientific discovery is, right? It's WTF. No, I've never, myself, when I've discovered something, or when one of my students, or one of my colleagues when I was a grad student discovered anything, we never went Eureka. It was always, what the heck? Or, this makes no sense. Can you explain this to me? That's how scientific discovery sounds. So just to throw a wrench in. So, chlorine. Is chlorine going to be electron donating or electron withdrawn? Is chlorine electron withdrawn or electron donating? So, chlorine is electron withdrawn because it's more electronegative than carbons. So, chlorine is an electron withdrawn group. And just to give you a quick example, for this reaction, the relative rate for chlorine is going to be 0.033. So its relative rate of nitration, which is all this stuff right here, its relative rate of nitration is going to be 0.033 compared to benzene. So it's slow. This is an electron withdrawn group. It's slowing down the reaction. So do you think, so for this nitration reaction now, so again, nitration, we use nitric acid and sulfuric acid. Do you think we're going to favor meta nitration or ortho and para nitration? What are we going to get? That's what you would think. But remember, I said I was going to throw a wrench in here, right? So things like chlorine and bromine